Well, good evening, everybody. I usually say on these occasions, welcome to the Department of Mechanical Engineering, but of course that's strictly not true on this occasion since we're in the Department of Civil Engineering. But anyway, we've taken over the Civil Engineering Department for the evening. Warm welcome to all of you, particularly those from Rolls-Royce, the sponsors of the Vibration UTC, which we've just had the celebration of the 25th anniversary. So we're here this evening to celebrate the inaugural lecture of Norbert Hoffmann, who's the director of the Vibration UTC. We're enormously grateful to have Norbert. It's been a rather tortuous process getting him here from Hamburg, but we succeeded. So inaugural lectures are great occasions because it enables us who are not in the direct research area to hear what our colleagues do and to celebrate their achievements and also, of course, to look forward to the future of the research field, so these things are both retrospective and prospective. So, Norbert, we're very much looking forward to what you have to say. You came to us, as I said, from Hamburg, having spent significant time with Bosch in Germany before that. So, a nice mixture of academia and industry, and a nice mixture of fundamental and applied research. So, we very much look forward to hearing what you have to say. So, Norbert, over to you.
Thanks, Peter, for the very nice introduction, and thanks a lot, especially for having the chance to give an inaugural lecture of this kind here in the college. When I was setting it up, I was really thinking, well, what is an inaugural lecture about? And I looked back to the Romans, actually. Augurs were people who looked to the flight of birds when some special things got started, say when a crusade was gone or a military activity or so. And then people were looking for signs of good omen. And why did they look at birds? If anybody of you has ever been to Rome in the wintertime or so, then you will definitely know why they looked at the birds. There are these tremendous swarms of the birds around there. And if you see them moving, then you can get an impression that they are really about to tell you something beyond what you know already. So the examination of birds' flight has a very, very long tradition. And in that sense, basically, I will try to do an inaugural also for my own field here. So I will really essay to have a view up to the sky to all these things which are a little bit beyond, maybe. So you may say it's a bit bluish, so it will be very bluish today, this lecture. And so let's get it started and let's do an inaugural, actually. And it really starts with having a look at birds, basically. Hope that the sound is also on now. I think that's about a good start. So what do I want to take out of this lecture? Basically, my topic is vibrations, dynamics in mechanical systems, mechanical engineering or so. What is this about? It's about motion, forces, things changing and so on. And this is, of course, a topic of antiquity. Yeah. So if you look back also to antiquity, then you will say that most of the philosophers, of the natural philosophers there, said that everything was in motion all the time, everything is changing. There were only a very small minority saying that there is no change in the world. And also, this topic is really intricately linked to flight, actually, and engineering. And that's quite interesting. Here I have two graphs and pictures of Daedalus and his son. And of course, most people know the tragic history of the son more than the history of Daedalus. Daedalus was known as one of the most famous engineers of his time. He's said to have invented the saw. He's said to have invented the stage, the labyrinth, and many things. Actually, also statues, which were said that they would move on their own if they hadn't been chained to the wall and kept there. So actually, sort of robot-like structures already were said to have been invented by Daedalus. And of course, the birds of these days look different. So usually we are now looking at these wonderful airplanes, and say about 2,500 years later, one could say this stream has really come almost true to a very large extent. And of course, our everyday work on vibrations and dynamics, that's usually related to these objects related to these planes out there. So you can see these wonderful engines down there really delivering the thrust. But then I thought, well, I'll do it a little bit differently here in sort of approaching the topic of dynamics, or what is it all about. And then I looked to what is out there in the media. And out there in the media, vibrations is not sort of the sexy, high-skyping topic, I would say. So if you look to Germany, for example, then in mechanical engineering, there's often this talk in the town on the fourth industrial revolution, on the Internet of Things, on cyber-physical systems. And so I'll try to do two little loops actually here from looking at what is really out in the media on these topics and link it on the first dynamics, vibrations, mechanics, so the physical side of it, and then to aspects related to the human interaction with these objects. So let's see how this goes. So the Industry 4.0 is quite interesting. I don't know if many of you have seen this. So there's a lot of talk on this, saying that there was a first industrial revolution, which is basically related to mechanical energy, steam engines, and so on. And Imperial is a wonderful place actually to have a look at this, since you can just walk out here, turn to the left, and then you can have a look at these original steam engines from exactly that time. Then the second revolution, they say, was in the 1870s, division of labor, electrical energy, mass production. Also quite an interesting place in here. If you walk out, turn the other way around, walk up to the park, then you can see sort of the remnants of the great exhibition of 1851, which was just at the verge of the origin, actually, of what was happening there. The craftsmanship was still sort of dominating, but just a few years later, everything sort of turned over. And then third revolution, 1960s or so, that's the IT, the computer. And actually, yes, this is true. It's about the 60s, I would say, when computing had started. And that's also about half a decade, half a century already, almost now. Half a century we are used to using computers. And so now they say there's a lot of talk on cyber physical systems and relationships to this. And popular pictures look like that then. You have lots of objects and they are all interrelated. and of course, we are all used to that these days. Everybody of us has one of these smartphones somewhere. And then you can turn off your heating system and all these things. And that's the Internet of Things discussion sort of going on. Now, what I always get distracted on this is, where is mechanics in this? Where is the physical world in this talk on the Internet of Things? So does this not play any role anymore, or where has it actually disappeared? And if you go to the media and have a look at this and take some statements and slides from other places, then you get statements like this. Okay, there are these cyber-physical objects, and there is control involved, computation, communication. But here, for example, on this graph, you don't see any mechanics, any physics involved anymore. It is completely gone. Yeah, it's not there anymore somehow. Then, for example, if you look for statements that people from software engineering really do, then they say, okay, there was a time when the systems sort of got along without any software. Then they got a little bit interconnected. And now, actually, there is even more interconnection and intelligence related to it. And we have what they call the Internet of Things and Services. And funnily enough, there is not even in the beginning there is a talk about physics or mechanics or anything like that. Yeah. Okay, so I don't want to sort of put all this down, since of course this is driving the world around in the public outside. And another graph here showing what the cyber-physical world is really looking after. And then we are getting a little bit closer to topics that also in mechanical engineering, in dynamics especially, we are looking for. So there is big data out there. And of course also here in big data, we know, or we encounter this more or less in our everyday communication already. But there is also something into mechanical engineering. Big code, behind that, of course, there is also engineering computations. And then you can go through this, but still very hard to find where sort of the mechanical engineering is sort of in this whole picture. So it's hidden in there. Maybe it's everywhere. Maybe it's nowhere. I don't know. Okay, and so the question really is, so I'm a physicist by training, so Peter introduced that already, so I then have grown in engineering, and the question is, should I be very disappointed about that? And what are people thinking about physics these days out there? What is the young generation having to look at? What are these two guys, for example, just taking two physicists? What would they say about that? Well, this Englishman looks a bit skeptical. Yeah? I mean, he did a lot of other things in his careers also, so probably he wouldn't be too much surprised. The Austrian on the right-hand side seems to be much more easygoing on all this. I mean, he was always said to have also a focus in good life, of course, and actually also in his later career stages, he actually worked on what life is actually also in a scientific manner. So this is where I want to jump in and have a second look at mechanical systems, at vibrations actually. Are vibrations, is dynamics really so sort of non-intelligent? Is it so stupid in a sense as we often, as it seems, or as many people in the outside world are looking at it? And as the model systems, I will use these friction brakes that I've been working on for really about 20 years now. And you will find them everywhere, and actually they are quite important objects, since normally, of course, people talk about propulsion, but also you have to decelerate, and then in ground vehicles or so, even in mountain bikes or so, you everywhere find these friction brakes, up to airplanes, of course. And first, now I'll just present a few findings which make one doubt a little bit that the mechanical and the dynamics perspective, the world of dynamics, is really so simple as it's always presented. First example, that's friction noise. That is basically what you can also get when you just take your hands and rub it. Yeah. So what you hear is a broadband noise. You would say it was a random signal for some reasons, hardly hard to characterize or so. And if you analyze that from real-world friction brakes, then you will find out that over a certain cycle of operations, a certain number of brake applications, well, actually this noise changes a lot. It really changes a lot. So when people design friction brakes, then they assume that the friction coefficient, the braking power in a sense, always stays constant. But if you look to the vibration characteristics of these systems, then you find out that basically it looks similar when you follow a small number of these brake applications, but if you do, say, 100 of them, then you can't really recognize anything anymore. So there's a complete change in the system behavior. And of course, as a mechanical engineer, you would say, okay, there's wear behind this, and so surface properties are changing and so on. But it's kind of surprising, this kind of discussion, that there's this ever-changing state in the background of the system, and at the same time, we rely in engineering on having a controlled sort of friction force resulting from it. That's not really in the design processes. Nobody looks at this really, in fact. So there's very often a permanently changing state in these dynamical systems. And the same thing can, for example, also be found when you go to assembled and built up structures where you have lots of components and they are interlinked with joints and so on. And then if you look in detail in there, then you will find actually that over time, over load cycles or so, these systems very often do not really sort of shake down or settle down to some sort of equilibrium state or so. So for me, this is a bit tempting to think that maybe we are a bit spoiled from our engineering education, starting with static systems, equilibrium solutions, and so on. Maybe the world is a little bit different there and actually changing all the time a little bit, yeah? And we're just not looking at this actually. If you go deeper into that, then for the same data, and by the way, here again, this kind of data analysis comes up, then you can analyze that, for example, with techniques that people in physiology or medicine use. You just put what is called a recurrence analysis on it, and that's just a very simple technique just to see when sort of the vibration sort of recurs, comes back. And then you find that this simple looking vibration result, which is in there, really has very complicated patterns. And when you change the sort of the brake applications or so, then you get really tremendous changes in this internal state. Still, the friction coefficient, what we use in engineering, is the same. Still stays very much the same, no change in there. But the internal dynamics is changing quite a lot. It's quite interesting to see that it seems that we are very often in our in our perspective towards these technical systems, we are not applying these analysis techniques yet that other people in, say, the life sciences or so do apply already. So interesting, hardly followed up at all at the moment. So then, of course, there are simpler things. Most of you will know Flutter and things like that. Here I bring an example of a squealing friction brake. I hope it's not too loud. No. So this is what you know from your mountain bike or so, for example. The people in the automotive industry know it. When they brake, then the thing starts to squeal. And the interesting thing in here is basically that this is a very simple example where you can see that a system can either be in one state or in another state. And what is found out recently is that very often all these systems have not only two states, but many, many different states that they can settle into. Many, many different states. And it's not at all clear sort of which of these states it's going to be. It's a very complicated question, which is not at all sorted out. And if you think that that's just sort of a playground aspect, you can have a look at this one. This is also a project that I've been following for a couple of years. That's a squeaking hip joint, an artificial hip joint. So this is, maybe some of you might have seen this advertisement for some grease or so, where there's an old lady marching in a supermarket, and then actually they put grease on the shopping cart, and basically it's not the grease. But that's not true, but this is a real video, and the company behind it definitely wouldn't like to see that, actually. Anyway. Coming back to the underlying question, if you really go into studying these different states, then you find out for more and more of these systems that actually there's really a large multiplicity of possible dynamic states. And sort of from this simple picture of having one dynamic response to sort of a turbulent response with lots of complicated states, so there seems to be a large transition zone in between, which is not really investigated in detail. And even our techniques are not there at the moment to follow this up. Multiplicity of possible dynamic states. Then you can go beyond sort of this purely temporal evolution and look into patterns. Of course, this is also an old topic. Also started, I would say, at least in the 1960s, maybe some precursors in the 1940s. And everybody knows this from the teacup. Yeah? So if you look into the teacup and pour some milk in there, then you get these nice patterns on there. Yeah? And so I was lucky to work sort of on all of these four applications here. Convection rows on the top left, boundary layer instabilities on the top right, and also a little bit on dust roads, where for example, when you drive over these dust road streets here, then ripples do form spontaneously. And what is interesting is here that basically, for example, the wavelength of these ripples is not sort of given by the outer forcing or anything like that. No, it's the physics, the mechanical system itself, which chooses to pick one of these possible patterns. And there can be many, many of these patterns, of course, also. So there is this pattern formation perspective to it. Slight shift again. Of course, you can have waves. Waves are also sort of patterns. Of course, they do come about by interaction of wind with the ocean wave state or so. And then these water waves, for example, are a very nice example for what is called rare and extreme events. Of course, the media are full of that also. So you have extreme weather events, so there's an extreme flooding, extreme rainfall, whatever. Yeah? And so I've been working for a couple of years on extreme water waves. And what you see down here, that's just sort of a time series of a recording at one of the oil platforms in the North Sea. And there was quite a heavy sea state already, plus minus 5 meters. And then here, all of a sudden, you see that there is a wave with a sort of crest to trough value of about 25 meters coming out all of a sudden. And this is, of course, a big debate. How do these rare events emerge? How are they related to all this this stuff? And it's actually just a rather recent finding that you can have these kind of events really emerging sort of from nowhere and disappear to nowhere also. So this a dynamically new insight, if you like. And here is some own testing data from our labs, wave tank data, where you see there's a small wave with a very small perturbation, then this blows up and you get an extreme wave a while downstream. And it's hard to sort of imagine how this looks like. For that, I brought a small movie here also. To visualize it, we put a small, I think it's a Lego toy boat or so. Yeah, it's a pirate. look it up at YouTube. I very much encourage you. This is my most cited YouTube video. So we put this toy boat in there, and then we sort of put in exactly the small perturbation, which could be as small as you would like, and watched how this extreme wave, this rogue wave on the ocean, in our case, in our wave tank, evolved. And now you can see it coming, actually. So a very harmless background state. And then here you see the big wave. Capsized, yeah. All you have to look is for YouTube, pirate, rogue wave, then you find this. Okay, to sum this up. Looking at dynamical states in mechanical systems alone, actually, I would say there is nothing really like an equilibrium solution. These systems are actually always changing somehow a little bit. Then, what we've seen from this pattern formation discussion, well, there are really new sort of patterns and states coming about all the time. Then we see that these states are usually not alone, but there is a large number of these states coming about when you look to these sort of typical systems which are characterized by nonlinearity and complexity in terms of sort of size. And they can really evolve in a quite vicious way. Yeah? So these, they can really sort of take a turn at a time when they just like to. So it's not like such that you really have the clear, traditional, intuitive understanding of determinism, or such that have your initial conditions and you know where you go. No, it has been found out really that these solutions can be parallel to each other and then will just go off to the side. That's possible already in mechanical systems. And now, of course, well, this doesn't sound so stupid, actually, or so unconvincing or non-intelligent, I would say. If you compare this to terms which come about from the life sciences or from the cognitive sciences or so, you could say, well, maybe these brake pads that we have in our cars, maybe they are actually learning all the time. Maybe they do this on purpose for some reason or so. Maybe there is some plasticity in that context in there. If you look for these phenomena, well, maybe there's really the wish to really create some targets out of these mechanical systems, some ordering and pattern formation. Multiplicity of states, well, the systems have to choose somehow. It's a matter of choices in a manner. And spontaneous evolution, this probably needs another one, another fresh look at what determinism actually means. And surprisingly, I'm not a natural philosopher. I'm not from the philosophy of science. I'm not from IT and so on. But there is very little work or discussion on these aspects. Everybody of us would probably say, okay, all this does exist in biological systems, does exist in computing systems, everywhere it is. But in purely mechanical systems, we don't have a big discussion on this. So why is that? Isn't it strange? I think it's a bit strange, and so I guess, and I would bet that actually there will be quite some surprises about this coming out in the near future again. Okay, so that brings me to the second half of my talk. Okay, this looks good. I'm quite well in the timing. So let's start off the second part. First part was on physics. So some of you might have recognized that. That's a classic, actually. It's 1970s. It's Kraftwerk. Basically, they are famous for electronic music. I mean, groundbreaking. Actually, now they get art exhibitions done for them since they have really inspired this electronic music scene so much. But the interesting part in this is, of course, where is the human sort of in this whole discussion on the Internet of Things? What role is the human playing? And just to open this up again, this discussion or this story. I like movies very much, so I brought two movie topics back here. First one is transcendence. So this is about copying the mind into a computer and sort of getting over death by that. So isn't it striking that physics doesn't play any role anymore, seemingly in there? It's just about the mental side of this, what would we attribute to the human. The other way around, at least in this movie, in this film, the other way around, of course, there are the robots in a sense. Also a very recent one, just a few months old or so. There is this debate on what the robots and what artificial intelligence and all that is going to move to and what it can actually reach. And it's an interesting link to physics. Quite a lot of people get worried already about these robots. Well, maybe that guy just got worried since physics is not on the headlines so often anymore. Could well be. But at least he's stating that actually this artificial intelligence could end mankind and overcome our species, in a sense, somehow. Well, this is not a new story. Many of you will recognize this one here. I think it's 1960s or so. And the most famous statement from this movie actually is, sorry, Dave, where are you, Dave? Can't do that for you. And if you go even further back in history, then you see that these thoughts and ideas, they have been there for a very long time. Middle Ages, the golem from the Jewish tradition, where sort of from clay or so, and by some magic, this golem man-like creature was created. And back into antiquity, I mean, this is Pygmalion. Pygmalion is another one of these famous creatures where sort of you have a sculptor which is able to generate an object which then comes to life. Actually also attributed to Daedalus again, who was the inventor of the saw, in a sense, of the mechanical systems. Quite interesting analogy there. And of course here in this place, of course, there's a new story on this, a rather more recent one. You find this coming back all the time. So this is an everlasting story. So you could say, okay, nothing new in this world, nothing new under the sun. These stories have always been there. But, well, things do change, actually. Things really do change. And what you see here is a feather. So we are back to birds, by the way. This is an inaugural. We're looking at birds. So this feather is the famous feather that a Mr. Meyer found in the 19th century. And it's a fossil feather showing that actually the birds might be related to the dinosaurs. And on the right-hand side, that's the famous and widely known Archaeopteryx, the English one, which is again related to this story. And even when it came over here, then actually Darwin put it into a second edition of The Origin of Species, that actually things do change by evolution and things like that. So maybe, well, I'm falling too short with saying this is all nuts with this artificial intelligence there. Maybe it's not true. Okay, coming back, what are our software people saying about that? Then you find pictures like this. So now at least this makes me smile, since there is a physical space involved, at least on the right-hand side. And then the human being is sort of interacting rather with the cyberspace, and the cyberspace somehow has this physical space in the background only. Yeah? So I would argue very much stronger that this is probably not a right cut over there, and maybe the physical space will have quite a lot to offer also, but this is how they very often propose it. And at least they do bring back the human interaction sort of into this whole game. Looking back to mechanical engineering, well, you all have seen these representations. Maybe you have also used that already. This is virtual engineering in terms for an auto company or so. And these two lucky guys there, they are really moving around this lamp and putting it in place. And what I find intriguing in there is that this is really very much like sculpting or so in the old days. So they are standing there and then they use their intuition and actually move the stuff around and bring their own sort of gut feeling and non-rational capabilities also into the play. At the same time, this is only geometry what they are dealing with here. It's only geometry. And so now I'm from vibrations, from dynamics, so I'm interested in how things do change. And I think there's no dynamics involved in here. This is only pure geometry, objects which have a certain form and shape, and that's it. Yeah. And if I then ask myself the question, well, these are the objects that I'm really interested in, or that many of you ask me to work on, actually, then there is quite a gap in there, actually. And will we really be able to bridge this gap someday to have sort of what those two people have been doing on the geometry side, also on the physics side, basically, someday. Okay, and this brings me to another sort of story. Let's have a quick look at computing. Yeah? So the computing story, especially when you talk about it in the outside world, that always relates to Moore's law. So you see how the computing power goes up exponentially. So there's a logarithmic scale here. Over the years, there's almost a straight line. And you see, well, looks terrific, looks wonderful. Yeah. And recently, I've been sitting with some of the chaps from the British Meteorological Service. And after, I don't know how many beers, I dare to ask the question, how much is your predictive capability going up? And how much has it gone up over the last 15 years? And then they came out and said, okay, 10 years, no change. 10 years, no change. And if you look into the topics that we are looking at, finite element analysis or so, mechanical dynamics, then there is a similar sort of perception sometimes. So although we are getting larger and larger computers, we are having severe difficulties in really getting this one, what you see there, getting this sort of into flight, yeah, sort of making use out of this. And why is that? Well, there is an intense debate going on, and I just sort of try to report this here with my interest in dynamics and mechanics, and I think I should report it in here since this will put me out of business either, or it will really cause me some trouble if I won't do this right as a vibration and dynamics person someday. What many computing people say, okay, one thing is the compute bound. That's what Moore's law tells us. The other thing is data handling. And if we don't get better solutions for data handling, then actually the time it takes to really sort of move data around in these computing systems, that will actually limit all our computational capabilities someday. And they are really not so worried. I would not dare that, but they put down the algorithms and say, okay, say in 10, 15 years or so, we will not have the slightest chance to use these computing facilities anymore, and things like finite elements or finite volumes are involved there then, and say, okay, this won't work anymore. We need to change to completely other algorithms. We have to change our algorithms on all levels just to get over this sort of memory roof, they call it. Compute bound is not the limit actually anymore. And then they also distinguish between weak scaling, strong scaling things. So there are these problems like weather or very large scale natural science problems or so, where you just have large problems and you have to crank them through. It's not so much a question of how quickly you can do it. And then there are these weak scaling problems where actually you don't need to have these very large models or many degrees of freedom. You just want to have a decently sized model with a lot of physics knowledge in the background, and then speed this up such that ideally, in the vision, you could reach sort of an online simulation of a machine, say a combustion engine or a gas turbine or things like that. And that smells very much like a paradigm change, sort of lurking in the background there. And I don't claim that I know what is going to happen there, but it really is something that one needs to look into and do some small steps actually to see what's going to happen. And the paradigm change would be quite drastic. If the memory problems turn out dominating, then that might be that the traditional approaches of co-simulation that we all use are actually really limited, and we will need to go back to sort of a completely alternative, integrated approach of tackling our problems. And this, of course, is something when I thought about this, and I said, okay, this sounds very much like what everybody did in the 1960s. So there was a problem that was solved very specifically. You used every algorithm that you could get hold of, and then you used the largest and smartest computing technologies. That was the 1960s status, and there were no general purpose computation tools. And say 15 years ago, I would have said that's all dead. Yeah? Since we have these general purpose tools, and then we use Moore's law, and then we just have to wait and see how this all goes. And there is a scenario here which suggests that this might turn around again. And if you really want to compute quickly the complicated problems, then you actually will need to go problem-specific again, combining all the physics and all the specific physics elements, like those that I've tried to sort of sketch a little bit in the first part, with the modern and the newest computing techniques. Interesting and challenging perspective. Well, we'll see what happens. Just as an example for how well this way may work, actually, if you really put together the knowledge on the physics, sort of on knowing what you have to do for getting the right equations, reduce sort of model orders, and then put it in a correct or in a very smart and efficient way on computing fields, that's the C-state simulation here. We had a small chat on this beforehand. This is one of my interests in computing, and since although I'm not a computing person, I somehow got into this through the physics on the C-state. And what I want to say is basically today it's possible to calculate in real time a C-state, a reasonable C-state, on a few square miles, say 3 by 3 square miles or so. If you take radar data or acoustic Doppler data, put it into the computing system, then actually the capability for having sort of a concurrent, real-time C-state simulation is actually there. It does exist already. And it's not on the market yet, but it's clear that the American sort of military side is doing this already, and some commercial people are also after this. And this is quite interesting here, since this is definitely a topic where one probably would have said, okay, this is way too complicated. We will never get away with all the complexity of all the waves on the ocean or so. And I completely agree, you can't get away with it, but you can calculate it. You can just calculate it. And in a sense, this is one of these very small toy examples. I would say this is a small problem, actually. This is one of these small toy examples where you could really bring together the necessary level of knowledge on the physics with sort of these alternative computing approaches, and then really knock down problems where, say, 10 years ago, nobody would have thought that that's actually possible, and that could have been achieved just by waiting for Moore's law to evolve. And then it's getting interesting, of course. That's probably what one would like to get for machines someday. So that's what you would like to get for a car, for a virtual machine, for an aeroplane, for machine components or so. Yeah. And I'm very sure that this will happen. So no doubt about how this is going to happen, but this is going to happen. The other question is, of course, well, are we going to need the engineers anymore? Is this capability also going to make it possible sort of to our ingenuity and sort of the inventive power that we have? Is that also going to come up? And of course, there are people who do claim this. So also people in this room I know who do claim this. So let's wait and see. I pledge that we should, at this point, really be very careful. Okay, that's about what I wanted to talk about. I think there were quite a lot of very high-flying, bluish sky-type birds already that we have been looking at here. And I think this is a wonderful occasion now to really say thanks to the people who really deserve it. So I would really like to thank all the people that I've been working with and that I'm working with still today, either from academia and also my industry partners, both on the German side as well as, and especially here in London at the Vibration University Technology Center. And basically, these are really the people who make the things go forward. Yeah. And so I really feel like just being one of these many birds sort of flying up there. And so many thanks to all of you. So and after this look up to the sky, following these strange swarms of birds, I think then it's time really to go back to the everyday work, go back to small-scale work. And I think nobody sort of expressed that thought of going back to work better than Captain Kirk. Beam me up, Scotty. Thanks a lot.
Well, Norbert, thank you very much for a very wide-ranging and very stimulating lecture. I now call on Rick Parker, the Director of Research and Technology at Rolls-Royce, to give the vote of thanks. Rick.
Well, thank you, Peter, and thank you, Norbert. It was indeed very wide-ranging. We've gone back in history to the ancient times, to the Romans, and even before that to the fossilized days of early flight. I was pleased with your example of Icarus. I think there was something vitally important for the people in the audience there, that it wasn't flutter that brought it down, it was using the wrong materials. So at least, we got something right even in those days. You managed to get all 3 Airbus aircraft with Rolls-Royce engines, so well done for that as well. That's always, you get an extra drink for each plug for the company, so worth remembering. But you did two things that made me think I had a lot in common with you. One, you confessed to being a physicist, and I'm also a physicist trained here at Imperial College. Now, the one thing you don't know that I know is that standing in the middle of the City and Guilds tribe and confessing to be a physicist does not prolong your life. So it's never a good idea to be this side of the big divide when you confess to being a physicist. The other thing is you're a fan of craft work, and I also am, so that was nice to see as well, and nice to hear. You took us into the world of flight and the world of this whole world of manufacturing 4.0, which I know is a big thing in America and in Germany. It's only just starting to really catch on over here, this 4th industrial revolution. But it is incredibly important, but I think you grounded it for us very well, because there is a temptation to believe that providing you get the software right, the hardware no longer matters. The physics, the physicality of engineering is no longer the hard bit. And I think you put that back in context, and I think we need to spread that message much more widely. There are lots of things out there with some fantastic software that didn't exist a few years before, but they still, if you sit on your Apple phone 6, it still breaks in the good old-fashioned way, and that's nothing to do with the quality of the software in there. It's just, again, the wrong choice of materials or the wrong amount of the right material, whichever way you look at it. So we definitely have to keep grounded in the fact that good fundamental mechanical engineering, backed up by good physics understanding, is going to be important for a very long time to come. And I think the group you're leading here at Imperial epitomised that for me. As most of you know in the audience, but not all of you, we're celebrating 25 years of our University Technology Centre here in Imperial College. It's a centre built around understanding vibration in the real world, and Norbert is the third, or depends if you give Jeff Green credit for running it for a while as a temporary head fourth leader of this magnificent centre. And as Peter said at the outset, we were really, really pleased that Norbert was able to come here from Hamburg, and also from the Rolls-Royce point of view, very pleased that Imperial College managed to be flexible in finding a mechanism that allowed Norbert to have this bimodal life. I mean that in the geographic sense rather than any other sense, that he's able to spend some time, quality time with his family and friends in Hamburg, and yet devote some very serious and very high quality time to our work here at Imperial College. So I'll draw that to a close. I think there were some fascinating examples in there. I love your little Lego boat sinking. I'll definitely go back and Google that, so we'll have a look at that and show it to everybody. I remember up at the big wave tank they had at Edinburgh University, and the guy who invented the Salter ducks, Mr. Salter, he used to do something very similar where he could create a two-dimensional wave pattern in this gigantic waves tank with a tiny little boat in the middle, and the waves would be going everywhere, apparently quite randomly, and then suddenly this boat would jump 6 feet in the air from a water spike, the same sort of addition of Fourier components that cause these apparently random but certainly very disastrous events, and we suffer from that all the time in the real world as well. So thank you for a fascinating talk. Thank you for becoming part of our community here at Imperial College, and I think I can say that both with my Imperial College alumni hat on and with my Rolls-Royce hat on. So thank you for becoming a part of this wonderful community, and thank you for your inspired leadership of it so far, and long may it continue. Thank you.
Rick, thank you very much, Rick, and thank you for reassuring us that we're not going to be put out of business anytime soon as humble mechanical engineers. So that concludes the proceedings for this evening, so thank you all very much for coming. And I think there are drinks outside, are there?
I'm afraid not.
Oh, right, okay. Sorry about that. It was drinks beforehand, not drinks after on this occasion. Okay, well, thank you all very much for coming anyway.